In this video here, we're going to take a look at problems requiring integer solutions. Now we can use a simplex tableau method to solve linear programming problems requiring integer solutions. And we need to consider integer valued points near our optimal solution. And it should go without saying here, but just make sure then that you're confident with the material from the previous two videos within this chapter before continuing with this video here. So a very quick introduction here. We don't need to introduce anything new or anything like that. As always, really, the best way to demonstrate this method is to work through an example together. So let's not waste any more time then, and let's just get started with this example. So let's just get started then with this practice question here. Now for this question, what we've got then is a linear programming problem that is given as follows. So what we want to do here is maximize P subject to the following constraints. And as we can see then, the solutions to the problem are given as follows. So P here is 15.25, X is 5/2, Y is 0, and Z is 11/8. So for this question then, all we want to do here is find the solution to the problem, given that integer solutions are required. So for a question like this here, obviously the question that I'm presenting on the screen here is quite a bit easier than what you're going to get in an exam, because in an exam, what you'll get is, to begin with, context attached to the question, which instantly just makes it more difficult. But you'll also need to apply the simplex method. What I've kind of done here is quite the middle part of the question, right, which is applying the simplex method to just give us the optimal vertex here. Now, if the problem does require integer solutions, what we need to do then is just simply test points around the optimal vertex, which is this point here, right? So to do that, what I do like to do here is essentially just present the solution in the form of a table such as this one. So I've got the points here. I've got my two constraints here, as we can see them. I've got another column here to determine whether that point is in the feasible region. And then finally here, what do we get for the objective function? So what I've got here is my optimal vertex. Let's make a note here that this is the optimal vertex. So optimal vertex here. Now clearly we won't change y here because y is an integer, it's 0. So what I'm concerned about then is changing x here because that's a decimal, and same for, I should say the same applies for z here as well because z again is a decimal, okay? So what points could I choose here, for example? So for example then, I could choose, say, 2, 0, 1, okay? Like I said, the 0 won't change here, so 0 applies to all of these points that we're going to choose. The 2 is rounding down here, so 5/2 is 2.5. And then for 11/8, I don't know what that is as a decimal. Let me just quickly evaluate that. So 11/8, I get 1.375. So again, if I just round that down here, I get 2, 0, 1. Okay. What other points could we choose here? So I could also just keep the 2 here once I round down. So I get 2, the 0 doesn't change. And then here for the 11/8, let's just round that up, right? So I'm going to get 2, 0, 2, like so. What else could we do here? So I could round up the 5/2 then, 2.5 to 3. So get 3, the 0 doesn't change. And then for the 11/8 here, let's just round that down, right? So I get 3, 0, 1. Like so there. And then finally, we can also choose 3, 0. And if we just round this up then, I get 3, 0, 2 there, okay? And we'll go with these 4 points here, okay? Now what I need to check then is whether each point here will satisfy these 2 constraints, okay? Just notice then, these constraints here are what we have in the original problem. So, is 2x plus y less than or equal to 5? So 2 lots of x then is 4. Y here is 0, like so. 4 plus 0 is 4. And that is less than or equal to 5, right? So it does hold here for the first constraint. What about the second constraint here then? So x is 2. 2 lots of y is just 0. And then 4 lots of z, so that's 4 times 1, which is 4. I get 2 plus 4, which is 6, which again is less than or equal to this value here, which is 8. So it satisfies both constraints here. So in that case then, it does lie in the feasible region. So I'll just put yes here. Or you could also give it a tick across if it doesn't lie in the feasible region, of course. And then in that case here, what is the objective function here, right? Which is to maximize P. So p here is equal to 5x plus 3y plus 2z. So in that case then, 5 lots of x here is 10. So p is equal to 10 plus 3 lots of 0, which is just obviously 0, plus 2 lots of z, so 2 lots of 1, which is 2. What we get here then is 12, right? I'm kind of running out of room a little bit there, but it doesn't matter too much. Hopefully you can just about follow that. So this here then is the first row complete. And basically at this point here, we just need to repeat this process, right, for each individual point. So let's just keep going then. So what about 202 here? So again, does it hold for this constraint here? So 2 lots of 2 is 4 plus y, which is 0. So we get 4 plus 0. And again, it does hold. Like so. What about this constraint here? So x then is 2. 2 lots of 0 is just 0 again. Now 4 lots of 2 here would give me 8. So I get 2 plus 8, which is 10, but clearly 10 is not less than or equal to 8. Okay, so it's not less than or equal to 8. So in that case, then it doesn't hold for this constraint here, and because it doesn't hold for this constraint here, then in that case it does not lie in the feasible region. So I'll just put no here, and in that case, then because it doesn't lie in the feasible region, there's no point evaluating the objective function, right? So we'll just leave that blank. Okay, I'll put a cross there. We don't need to bother with that. Again, let's just keep going here row by row. So for this point here, what do we get then for this constraint here? So 2 lots of 3 then is 6. Now clearly, straight away, this constraint here won't hold, but I'll just go through it in detail. Plus y, which is just 0. So I get 6 plus 0, which is 6, and clearly 6 is not less than or equal to 5. So in that case then, this constraint here does not hold. So we don't need to bother with the second constraint here, right? If the first constraint doesn't hold, then in that case, it definitely won't lie in the feasible region. And at that point, we don't need to continue, right? We're just kind of going through the motions for no reason. So let's put no there. And again, just give that a cross, right? And then for the final point here, 302, again, we just repeat this process, right? It is a little bit tedious. I do appreciate that this is not the most exciting mathematics that we've ever seen, but it is pretty straightforward. So let's just continue then. So again, you can probably see already that this constraint here will not hold, right? Because again, I get 2 lots of 3, which is 6 plus 0. And again, this is not less than or equal to 5, right? So again, it does not lie in the feasible region. And as we can see then, that just leaves us with one solution here in terms of the objective function. Sometimes you'll get multiple values here, and clearly if we want to maximize p, we would choose the largest of those values. If we wanted to minimize p, we would choose the smallest of those values. But in this case here, I've just got a single value, right? P is 12. So in that case then, let's just write this underneath here. Therefore, the best integer solution, so the best integer solution here, the best integer solution is, so what did I get for p here? So for p then we got 12. So p is equal to 12. What about x then? So x here, so that corresponds to this point here. So x is 2. Y is just 0. And then for z here, we just simply get 1. Okay. So as we can see then, the process here of finding integer solutions is pretty straightforward. As I mentioned before, I do appreciate that it's not the most exciting area of mathematics, but really, is decision mathematics that exciting anyway? Not really. So nothing too different to what we've seen before, right? But there we go. So the best integer solution is the following, okay? And there we have it then. So that gives us the solution here to the one practice question for this video. And that brings us to the end then of this video here on problems requiring integer solutions.